So this is 3.3, the empirical rule, and the goal for today is to be able to represent data using the empirical rule. So we'll start off by kind of defining the empirical rule. It's used for all bell-shaped distributions. So for any quantitative data set, with a roughly bell-shaped distribution, the following properties hold. So that should sound familiar, right? Bell-shaped distribution, we've talked about that. We've talked about quantitative data. You see how it kind of builds. So the empirical rule states that for any, again, quantitative data set, roughly bell-shaped distribution, there's three properties that hold true. Approximately, notice that word approximately, 68% of the data falls within one standard deviation of the mean. That's represented by the x bar plus s and the x bar minus s. And then property 2, it's really tiny. There, so property 2 says approximately, again, 95% of the data lies within two standard deviations of the mean. That's the x bar plus 2s and the x bar minus 2s. S, remember, lowercase s stands for standard deviation. And the third property is that approximately 99.7% of the data lies within three standard deviations. So between x bar minus 3s and x bar plus 3s. If you got a 99.7% on a test, you'd feel like basically at 100%. So nearly all of the data is nearly 100% is within three standard deviations of the mean. So we'll take a look at this visual depiction of the rule. This is kind of what comes to my mind when I think of the empirical rule. And you see the x bars right here in the middle of this distribution. Remember when we started talking about distributions, those relate back to histograms? So like bar graphs, right? So you can kind of picture that behind the scenes of this curve, there was once a bar graph where the middle would be the highest point, which would be the mode, the data point that occurred the most often, and so on. So you can see here that x bar lines up with the mode. The mean, median, and mode are all equal when we have a normal distribution. And you see the 68% right here is within that one standard deviation of the mean. So here's the x bar, you add an s, you add a standard deviation, subtract a standard deviation, and so within this part of the curve, we would expect to find 68% of the observations. And then if you add the 2s and subtract the 2s, so two standard deviations away, we can expect to find 95% of the data, or the observations. And then the 99.7%, notice we still have a little bit of that tail going on, right? So between the minus 3s and the plus 3s, almost all of it, but not quite. There's that little tail that kind of goes on forever where part of the data will lie. And when you hear things like you're listening to the news and they're talking about 95% of the data, oftentimes it relates back to the empirical rule. Even as election season comes up in November, next month, you'll hear things. It's going to totally connect to your understanding in stats, and you're going to go, oh, now I know what that means. So the other thing that I think of when I think of this curve, I think about IQ, and like where you stand in terms of IQ is often referenced, where it's not on a scale of like 100% is the highest IQ. It's what we call norm-based, or norm, where we reference like an average instead of like on the scale of 0 to 100%. And similarly, when you go to the doctor and they tell you that your 2-year-old is above the 99th percentile in BMI, body mass index, which is the weight to height comparison, that's norm-based reference as well, where they're comparing your child to all the other children her age. So this is from this morning. She is above the curve. She has been above the curve since when she was born. She was at the bottom of the curve. She was teeny tiny. Oh my gosh. She does know it. She's feeling it. So, referencing the curve. She's in this little section above right here when it comes to that weight to height ratio. I think I'm really proud of her for that. I know that that's not always going to be a good thing, but at this point in time, I feel good about it. So there you go. There's that real life connection for you. Another real life connection we have here is this example, PCBs and pelicans. So PCB is this polychlorinated biphenyl. It's an industrial pollutant. So like industrious activity kind of creates this pollutant known to be carcinogens and a great danger to the natural ecosystems. And you can see here several students, love that, got that PCB banned in the U.S. in 1979. And then by the Stockholm Convention on Persistent Organic Pollutants in 2001. So then there was this study published, and we see here is the data from that study, and there were 60 Anacapa pelican eggs collected and measured for their shell thickness in millimeters, and they tested those shells for the concentration of PCBs in parts per million. And the PCB concentrations are presented in the table. Now this is more of a realistic size of a data set. You can see there's 60 observations, and we need to calculate here. We're going to calculate the standard deviation, but first we're asking the question, is it reasonable to apply the empirical rule? So this data is actually laid out for you in this histogram. Does that histogram look relatively bell-shaped? It is. We can apply the rules of the empirical rule, or the properties. So we'll write yes here. And then use the empirical rule to estimate the percentages of observations that lie within 1, 2, and 3 standard deviations to either side of the mean. So you need to type all 60 values in to Google Sheets and calculate the mean. Just kidding. I did that for you. So the mean.
Thank you.
You're welcome. It was going to be unnecessary. You all know how to do it, right?
All right, here we go.
I just don't feel that is necessary right now. So we're going to just go ahead and let you know the answer is 206.45 is the mean. And the standard deviation is 66.42. And both of those are parts per million. I'm going to draw a really long horizontal line here because the numbers have a lot of decimal places. And I'm going to draw a line in the middle. I'm going to label that X bar. So without drawing the curve in the histogram, I'm going to use this horizontal line to help me keep my numbers straight. So I'm going to calculate my X bar plus S, X bar plus 2S, X bar plus 3S. And similarly on the other side, X bar minus S, X bar minus 2S, X bar minus 3S. I just basically copied the horizontal line from my empirical rule picture above. And I'm going to fill it in. So X bar 206.45 goes in the middle. And then if I add, so go ahead and calculate. You've been calculating on your Math Excel, just get out your calculating device and type in 206.45 plus 66.42. Shout it out when you got it. 272.87, thanks. 272.87. And then on the other side, do x bar minus s. So 206.45 minus 66.42. 140.03, good. And then what percent of the data would I expect to find within the range 140.03 to 272.87? What percent of the data? 68%. 68% of those eggshells observed would have between 140 and 273-ish parts per million of PCBs in the shell. Ashley?
So will that always be 68%?
Within one standard deviation of the mean, that is the approximation when we have a normally distributed curve. Yes. Liz? It's the rule.
So we just did it to find.
Mm-hmm.
Gotcha. What'd you?
So now we're going to add another standard deviation and subtract another standard deviation, which you can do by just adding another 66.42 to 272.87. Go ahead. Calculate that. Some of you are just ignoring me. That's okay.
What's the math for the That's just
Thank you, 339.29. And then on the lower end, we subtract another 66.42 from 140.03. Thank you, 73.61. And so within that range, 73.61, clearly I needed more room here, I would expect to find what percent of the data? 95%. I moved my table so that I could look. No, I'm not even looking to pay attention. Thanks. One more, right? Everybody this time. Anybody ever read that book by Jimmy Fallon, Dada? It's my daughter's favorite book right now. It's really good. It's just all the farm animals, and the dad farm animal tries to tell the baby farm animal to say Dada, and the baby animal just says quack or oink or whatever. And then at the end, he's like, all right, everybody this time, one more time, and they all say it. So that's what I'm saying. Everyone this time, calculate. It's her favorite. She walks over to it and goes, Dada! And she has like one word that she can actually say, and that's it. What? Okay. I will. Thank you. Anyone? Plus 3s, what do we get for this upper bound? 405.71, thank you. And the lower bound? 7.19. This is pretty spread out data. So with a standard deviation of 66, that's like an indicator that this is pretty spread out. So then we would expect to find what percent of the data within that range. Now you got it, 99.7%. Now the next question is going to ask us, in reality, how many of the observations actually lie in this range of 140 to 270. Remember, this is an approximation. So then, if we go back and we look at the data set, I'm just going to give you those numbers again since we didn't if we had put them in Google Sheets, we could just line them all up and say, oh, this is how many. It would be a pretty quick process. But we didn't do all that. So we're just gonna jump in and say, use the data, that's the key, not just the rule. So within 1, 2, and 3 standard deviations, so actually 43 of the 60 observations lie within 1 standard deviation of the mean. So 43 divided by 60 times 100, the percent of observations that lie in that range is actually 71.7%. We're comparing that to the 68, right? So it's a little bit more. There's a few extra observations within that first range of values. If we were to count them up, 57 of the 60 observations lie within 2 standard deviations. So 57 divided by 60 times 100 to find the percent. That one is right on. I drew my percent sign backwards. Percent. Sorry, that does not look like a percent sign. And lastly, if I look through that whole list and try and find how many of the observations lie between 7.19 and 405.71, if I look through here, try and find one below 7.19. None. Something above 405.71. So is there a 406? There's not. So all 60 lie within that range. So 60 of 60 observations lie within 3S. We don't need to write all that out. We know that's 100%, right? So 100% of the observations lie within the 3 standard deviations. If we compare parts B and C, right? So within 1S, the actual percentage is greater than the empirical rule. So we'll just say the rule. Within 2 standard deviation, the actual is equal to the rule. And then within 3S, remember the rule being 68%, 95%. Again, the actual is greater than the rule of 99.7%. Super close, though. In fact, on the front, if you want to write this, the empirical rule is also known as the 68, 95, 99.7% rule. At first it feels like it's hard to remember all of those numbers, but as you use them, they'll stick pretty quickly. You don't even have to work at memorizing them. They'll just kind of stick as we reference them so frequently. All right, I'm going to pause it here before I do the practice, and I'll pick back up.